Hi, can you all hear me? Yes, sounds like I'm on. Okay, thanks. So I'm super excited to be here today. So I am Caitie McAffery. This is where you can find me on the internet. But prior to working at Twitter, I actually worked at Microsoft for 5.5 years on video games in the .NET community and worked with a project called Orleans. And so I think Sergey is going to talk to you guys about that later. So it's really nice to be back in part of the .NET community. But today I'm going to talk to you about something that's actually kind of protocol and language agnostic. So let's get started. So back in the day, we used to sort of build these systems, these big monoliths that could horizontally scale out. And we had all of our sort of like concurrency and consistency problems were isolated to our single database. Often this was like a relational database like SQL. And things just sort of worked because we were at the scale where everything would sort of fit into one giant database that you could vertically scale up. That stopped being the case, and so we introduced this concept of like microservices and NoSQL for more availability and scale. And so we have these like systems that sort of look like this with all these different languages and all these different NoSQL databases with different kinds of consistency guarantees. And this has a lot of nice benefits, like we get higher availability with some of these NoSQL databases. We can scale out larger than one machine. We allow developers to operate in the languages that they like. And then also we like allow them to deploy faster. But it comes with a lot of challenges, right? Because now like we've sort of made our consistency and concurrency models much more complicated because all of our data is spread out all over the system and no longer in one database. And so Peter Bayless published this paper that's focused on Ruby, but I think introduces a term that I really like, and this sort of describes the world we live in today, called Pharaoh concurrency control. And basically, Pharaoh concurrency control is this application-level mechanisms for maintaining database integrity. And we'll walk through an example of what that looks like. But basically, it means the database no longer is our source of truth that enforces all of our consistency and concurrency guarantees and the invariance for our system. Instead, it's sort of spread out in application-level code. And so this comes with a lot of challenges because developers have to code this on a day-to-day basis. And it's easy to get wrong. So let's look at an example of how we might start building an application in our microservices architecture today. Say I'm a travel startup. I want to help people book hotels. So I'm going to have a hotel service which will have its own data store. And the invariant we want to enforce is that you have to have a hotel reservation before I will charge your credit card. And so the way we enforce this guarantee in code is that I make the hotel reservation. If I can secure a hotel reservation, then I will forward a request from the hotel service to like some payment API. And the payment API will then charge your card, et cetera, et cetera. But this is a Pharaoh concurrency control mechanism because a developer has to code the causal chaining of events in here of book the hotel and then charge the credit card. It also has to handle things like, what if we can't charge the credit card? Then I have to free up the hotel reservation that I held in your name because I couldn't charge you for it, and things like that. So this is all like, you know, bespoke, artisanal, developer-crafted code to enforce our system invariance. And so great, so we can do this and then say we're doing really well, so we want to help people book cars and we want to help people book flights, and this is how a architecture might evolve. This is totally reasonable. We can have different teams work on each one of these services. It scales very nicely people-wise, but you can sort of see that this is getting a little complicated. Now, product wants to introduce a new feature called trips, let's say, which allows the user to specify their location, dates, that they want to book for a trip, and then we'll just like go book it for them. And from a product perspective, or like if you've ever worked with product and they're like, why isn't this just easy? You already have all the parts. You can book a hotel, a car, and an airline flight. Like just go make it happen. It should take like 2 weeks. And you're like, not really, because first we're going to introduce this trips system microservice, which will have its own data store. And it's going to store all the information about the trip, which makes sense. But this has a ton of Pharaoh concurrency control mechanisms inside of it because it has to handle talking to all of these other services and what happens if one of them fails. It also has to handle the fact that what happens if the trip service processing your request fails in the middle of the transaction or the business request. It's not really a transaction. And so you hold some reservations and not some other ones, and like, what do you do there? You have to clean it up, otherwise you essentially have a leak. And so this is complicated code to write, and it's difficult to get correct. So it takes a long time. And so this is sort of like our resulting architecture for some fairly simple services that I've just like, you know, made for this example. You can sort of start to see how we end up with things like this, which are Death Star architectures. That is Netflix. That is Twitter. These are really common when you start having these systems evolve over time with microservices where they're like just sort of evolving because a team's like, I need a service here, and it talks to Cassandra, and I need a service here, and it talks to like Cosmos DB or whatever. And this is what happens, and they're really, really complicated and difficult to maintain, and they're more difficult to modify over time. Because you have to have a more holistic view of the system and everything it touches to understand all the different concurrency and causal relationships that are encoded in the system itself. Okay, so can we do better than Pharaoh concurrency control? These systems are really difficult to maintain and modify. So like, how do we make our lives easier? Because this gets like kind of crazy after a while. So what about Spanner? Spanner is Google's globally distributed database. They actually, I think, just GA'd it like last month. So basically, it's a Google scalable, multi-version, globally distributed, and synchronously replicated database. So it has transactions. It's essentially like running a relational database across the globe. The way they guarantee distributed transactions with 5 nines of availability is they have this thing called the TrueTime API. They have a massive amount of hardware, fiber between data center and GPS, and atomic clocks installed on individual machines, and a ton of redundancy. So that's why it really is a CP system if you're familiar with the CAP theorem, but they like say, like people, like their marketing department says it beats CAP, but that's like stupid. It just has 5 nines of availability. So that's really great and a great feat of engineering. So like, why don't we just all use this? Like, problem solved, right? Well, Facebook basically published this paper in 2015 saying like, probably not, because it's a 7-page paper, and I highly recommend reading if you're interested in this, but it boils down to the biggest barrier is that the consistency mechanisms must integrate across many stateful services. So part of the reason they're using microservices and denormalizing data is so that they can optimize all of their different like querying workloads to be really efficient. So they'll denormalize data in one format over here so that they can query it really fast for one use case, and then they'll denormalize it over here so they can query it really fast for some other index search. And they're basically going on to say strong consistency across all the systems would result in higher latencies because you're basically now bounded by the lowest machine or the slowest machine in your cluster. And they also posit that users will tolerate inconsistencies over high latencies. So Facebook is like, we're not going to adopt Spanner or even like some of these stronger concurrency control mechanisms like causal that are out there in research today and are known like sort of solved problems because it would add too much latency back into the system. Also, it's worth noting that like we already have this atomic commit protocol that will do distributed transactions across stateful services. It's called Twophase Commit. I'm going to run through it super quickly if you're not familiar. Twophase Commit, it has 2 phases. It's very aptly named. It has the prepare phase where everyone will say like there will be some kind of coordinator which will say go do this thing. Or like, can you do this thing? It'll propose it. Everyone will then vote and say like, yes, I can do this thing, or no, I can't do this thing. And then the coordinator, once it receives all the messages, will say everyone either go commit the transaction or abort it. And then finally, because it's a distributed system, everyone has to say I'm done. If that was a super quick run through, if you want to know more about that, Henry Robinson has a really great blog post about Twophase Commit on the paper trail that I highly recommend reading. But basically, the reason we do not use this in industry is because it doesn't scale. In the worst case, it has O(n)² messages. You have a coordinator, which is a single point of failure. So if the coordinator fails, like your transaction's done, you're gated by the slowest machine in your cluster not once but twice throughout the protocol. And it has reduced throughput because you're essentially holding locks in these systems. So while you do get distributed atomic transactions in the ACID sense, it has a lot of scale challenges. It's worth noting that Azure actually has a blog post specifically stating they don't implement Twophase Commit inside of Azure because it doesn't scale and for liveness reasons. And major RPC frameworks like Finagle and gRPC do not support this. So I think it's pretty clear that like we're not going to use this in industry because it doesn't scale for like very large use cases. For like one-offs where you have 1 or 2 participants and you're going to use this very rarely, it does sort of work, but does have known liveness issues. Okay, so instead I want to tell you all about a protocol that I've been sort of working on and using that came up in Halo when we started working on that in those days, and it's called distributed sagas. And the goal here is not to give you ACID transactions, but to help sort of simplify how we program and give you an understandable model and some very fairly strong guarantees that will help make building your systems easier. It's worth noting that we started looking at this in Halo for building the Halo statistics services and some other features that basically we implemented a very bespoke version of this that worked just for us. At Twitter, I've been working on integrating this within our distributed build systems And then also, it's worth noting that I went and sat down and talked with Uber because they were having this problem of their giant Death Star architecture and how do they modify and make more use of their services. And so they're actually starting to implement a version of this internally. And Matt Rainey talked about that at YOW 2016. So this is sort of getting some traction. So what is a Saga? Sagas is this idea that came from a paper on 1987 that was published, and in the context, it was just a single relational database. And the problem they were trying to solve is that sometimes you have these really long-lived transactions in a single relational database that take a really long time, but because it's a transaction, it holds locks, and therefore it becomes really, really slow. So basically, they say, what if we can break up these transactions into tinier sub-transactions, and then the sequence can either complete totally, like all of them commit, all these sub-transactions commit, or like compensating transactions are ran to, so basically the system is back in a comparable state to before the Saga started. So that's the relational or database, sort of single like machine relational database approach to this. And they sort of do this, the typical, 1980s distributed systems or database paper thing where they're like, oh, clearly this could be like turned into a distributed system. And it's like, cool, but that was actually a little harder than maybe just like taking your paper and implementing it. I came across this paper a few years back and found it interesting and was wondering if we could apply it and formalize it in a distributed system because we sort of care about the same things. We want really high availability and we want to preserve application invariance, and that is what the original paper is going for. And so this is I'm going to share with you guys some of the progress we've made refining it over the past couple years. So basically, a distributed Saga, we're going to define it as a collection of requests, so like our book, hotel, car, flight, and charging money, and compensating requests that semantically undo the request in the Saga, so canceling a hotel, car, flight, refunding money. And these things represent a single business level action. So either if they all complete, then the business level action was done. If you ran them and then ran all the compensating requests, then it looks like nothing happened in the system. So let's talk about the requests in a distributed Saga. What are some of the invariants that we have to enforce on this? Requests can abort, so you can say, hey, I'm going to book a car, and the car service can say, no, I don't want to do that because I don't have a reservation. That's totally fine. Requests must be idempotent. So this is basically the idea that if I run it multiple times, and then I get the response, that it has only happened once. And so that's fine, and that's great, because then if there's a timeout or some kind of failure, we can retry it in the system. The other reason we want, I mentioned this. The other reason we want requests to be idempotent is that basically, if I make a request, a timeout occurs, I want to be able to remake that request and have it be safe, and then only have it taken place once. Because when a timeout happens, that's our best approximation that a failure has happened, but we are not guaranteed that a failure has happened. So that request could get through. So if you were incrementing a counter, that's a non-idempotent request. For distributed Sagas and compensating requests, these have some other invariants that we have to uphold. Like I said, they have to semantically undo the effect of a request, but they do not have to roll the system back to exactly the same state. So some good examples of this is in our example, if I charge your credit card and then I issue a refund to that card, you actually may see two line items on your bill of I charged your card $500, I refunded your card $500. So your balance is semantically in the same state, but actually you see the effects of the two sort of requests in the statement. Another good one is if you send, say, a push notification or an email, you can't unsend that usually. So your compensating request could be sending a follow-up push notification or a follow-up email to correct whatever you said in the first one, to say hey, sorry, we messed up, here's a credit, or whatever. And so those are what compensating requests sort of mean. You can have these things that take place and have side effects in the real world, and as long as you're okay with a business level compensation for them, that is totally fine. Compensating requests cannot abort. So the reason this basically is that in order to provide the guarantee that we can always run them to completion, they cannot say no, I can't cancel this request. They always have to succeed. Compensating requests also must be idempotent. So this is the idea that I want to be able to rerun them until it succeeds, so that has to happen. And then compensating requests must also be commutative. And I'll walk through why, but commutative basically means that if I run book car and then cancel car, it's the same as cancel car, book cars. This is like addition. Addition is commutative. And so the reason we want this is that this is a time diagram. Time is going down. If something says book car, and we get a timeout because it got delayed in the network and it took too long to get there. We don't know if it got there or not. So I'm going to run book car again. That's totally fine. I'm then going to like maybe cancel the car reservation. And now my pesky first book car request decides to arrive. As long as our requests are commutative, we don't actually hold a reservation anymore. This is totally fine. So in summary, requests must be idempotent and can abort, and compensating requests must be idempotent, commutative, and cannot abort. This may seem like sort of a lot going on, but it's actually probably the minimum bar you need to have a totally like correct system. Most things it's common to make things idempotent today, so you can retry in case of failure. Canceling requests, I think we talk less about commutative properties on requests, but I think in order to cancel them correctly and not have weird side effects, they need to be commutative. We just don't talk about it as often. Okay, so if you have all of these properties with your requests, you get this guarantee that either all requests were completed successfully, if the Saga completed successfully, so your business level thing happened, or a subset of requests and the corresponding compensating requests were executed. So basically, like it's like the Saga never executed, so I hold no hotel reservations, no car reservations. Distributed Sagas, it's important to note, do not give you atomicity. You can see things that are happening as they happen, and does not give you isolation. So basically this means that if I go book a hotel and then someone else tries to book the same hotel, but I got the last room, they will be rejected, like their request will fail. But then I go and cancel the request because like charging my credit card failed, then the next person coming in can book the room. So that's what atomicity means. It doesn't mean that like people will see the intermediary states, but that's okay. That sort of like makes sense. Like the world is kind of eventually consistent, and especially in systems like this, you can kind of think of like where you can cancel or undo requests. It may just happen for other reasons as well. So this all sort of makes logical sense. And this is kind of the world we live in today. We don't have atomic transactions in a distributed sense across microservices. So basically it gets us back to this guarantee, which may seem weak at first, but I think it's incredibly powerful. Instead of having to hand code a bunch of custom Pharaoh concurrency control logic, we can simply focus on what we want our applications to do and define those requests. So how do we define a distributed Saga? Distributed Sagas at their core are just directed acyclic graphs. And so basically one of the things that this gives you, and is an extension of a previous talk, is the ability to sort of encode causality into the Saga. So you'll have things, basically anything that is, you start executing the Saga at the top and you walk down this graph, you can execute nodes in parallel as long as their parent, all the nodes in their parent route is complete. So you can execute car, hotel, and flight concurrently, but you can't charge the credit card until I have a car reservation, a hotel reservation, and a flight reservation in this Saga graph. Each distributed Saga vertex has a unique name, a request, like the information necessary to do the request, and the information necessary to execute the compensating request, and a status. And the status is the only mutable piece of state in this graph. And so there are two special nodes. There's a top and a bottom. I've just named them start and end Saga for sort of clarity. And basically, it's just special nodes. Their requests are all no-ops, and they're just to say, like, hey, here's where you start so you can have children, and here's where you end so that you know you are done. You also need a distributed Saga log to store intermediary state. This is fault-tolerant and highly available. You want to pick something that has, like, fairly high availability, because if you can't talk to the distributed Saga log, you will not be able to make any kind of progress in the protocol. And then finally, you need some kind of Saga execution coordinator. This is the thing that's actually going to execute your Saga DAG and make the requests. It's really important to note that, like, unlike Twophase Commit, you can actually have multiple of these things running per Saga. It doesn't have to be the same one throughout the Saga's execution lifetime. And you don't even have to have coordination to say there's only one working on it, because the requests are, in fact, idempotent. So I'm going to draw this as one on all the slides, but this could be many. It's like highly available because you can have multiple of them. Okay, so let's talk about really quickly how we execute a distributed Saga. So basically, we're going to start at the top of our Saga DAG, and we're going to get a request that comes in to say book trip request. It's going to have all the information necessary to book the trip. And so I start my Saga by basically saying, log a start Saga message to the log with any information I need to execute this Saga from the original request. And then once that is durably committed and responds that it is done, I can mark that node as complete. Then I can start going through and picking literally any, I could have picked car, hotel, or flight to execute, or actually execute them in parallel. That's like a performance optimization. For this example, we're going to go synchronously because it's easier to draw on slides. And so I'm going to just pick the hotel one because all of its parents are complete. It'll log a start hotel message to the log. Once that commits, I will then make the request to book the hotel request. And then once that happens, I'll get a response, it's going to work, and then I can log the end hotel message to the log along with any information that I made from the response that I might need later. So then I'm going to do the same thing for car, and I'm going to log in and make the request and then log the end message. I'm going to do the same thing for the flight. I'm going to go pretty fast through this just for time. All these slides will be online. And then finally, now I can execute the payment node because all of its parents are complete. So I'm going to start a payment, do the same thing, make the request, get the response, log it to the log. And now I'm at my end Saga node, and so I now know I'm done, and just I log an end Saga message, and then I mark everything as complete, and now our Saga has completed successfully. I hold reservations for a car, a hotel, and a flight, and I have been charged appropriately, and everything went fine. So let's talk about what happens when a distributed Saga fails. So say this is our Saga. What's happened here so far is we've executed the hotel, we've successfully booked it. We have a start flight message logged because we're running something in parallel, so we've started the flight node, but we haven't completed it. And then we're on our start car node, we're running that also in parallel with the flight, so we're gonna book the request. The car service is gonna say, no, I can't do that because there are no cars on that date available. And so now we're gonna log an abort car message to the log. At this point, once that's successfully logged, we now have to start rollback recovery because we know we can't fulfill our guarantee of you will have all of these requests executed to completion. So we're just going to start rolling things back and freeing any reservations we may have held. So in order to do this, we basically flip the graph. We flip all the vertices, the edges in the DAG. So the reason we do this is it holds some nice properties about causality. So like I can preserve my invariance that that there are no payments, or there is a car reservation if I've been charged and things like that. So this preserves some nice invariance by walking this graph backwards. So we're going to start at the bottom. I've renamed the nodes. Once again, this is just the top and a bottom of a graph. I've renamed the node start comp Saga. So I'm going to start doing that. That has no ops associated with it. Now we execute the payment node. We look in our Saga log. There actually are no messages logged, which means this node never executed. The request for this node never executed. So we can just mark it as completed and moved on. I'm now going to go to my car node because it's the same principle of I can execute anything that's parents are completed in this DAG. It's going to ask for the entries. There's going to be a start and abort pair. So I know that request never successfully completed, and there's nothing special happening there, so I don't have to execute a compensating request for it. Now if we ask the hotel for its log entries, I'm going to do get back, start, and end. Messages have been logged. That means I actively hold a hotel reservation, and so I have to execute the compensating request for it. So basically, the SEC will then go and make the cancel hotel request, which is stored in the Vertex, the hotel Vertex, on how to do that. I can use information that was stored in the end hotel request. So that's sort of a nice feature that we've extended and added with this from previous talks, because I am storing that data. So you can just say cancel the confirmation number that was in the end hotel request. I think that makes life a lot easier. And so then once that succeeds, I just log that I've successfully completed the comp hotel request, and then I can move on. And then finally, when I look at my flight, this one is kind of weird. I see that there is only a start entry logged there's only a start flight message logged in the log. And so now I'm like in this weird spot where it may have completed, it may not have completed. I'm not really sure what happened here. And so to be totally sure and totally correct of what happened here, I'm going to actually execute that request until it succeeds, and I get a response back. Because our requests are idempotent, this is totally okay. So once I get the response back that it executed successfully, I do the same thing where I log the end flight message, and then I'm going to immediately go and run its compensating action to cancel it. And then I can log that I've compensated for this flight. This seems a little weird, especially in like the flight example, but it is really the only way to preserve the correctness guarantee that we want. If you know that like you can sort of just send comp hotel request. There's like some variations you can get around it if you want to talk to me afterwards. But for like total correctness and a general model, this is what you got to do. So now I'm finally at my end comp Saga graph, and I just log that message because it's a no-op. And we still have our guarantee held that all requests were completed successfully, or a subset of requests, and the corresponding compensating requests were executed. So this is pretty powerful because basically all of this is held, all this logic is held in the Saga execution coordinator. It's not spread out throughout my entire code base. Okay, so I'm not going to go through Saga Recovery because of time. If the SEC can fail, and like I mentioned, it can literally be the same, it can be a different process throughout the life cycle of a Saga. You can actually just read through the log, rehydrate state, and then go figure out what to execute from there. That's totally fine. I don't have time to walk through that, but I hope you can see that you can basically always reconstruct the state of the DAG from the example provided. So let's take a little quick walk of how, if we had built our travel application with Sagas, what it would look like. So had I started with just my hotel request, I would have made a hotel service that only does hotels. And then I would also have my payment API. And I would create a Saga that says book a hotel and then charge the person for the flight. And that's totally fine. I would then go and add the car. So I would just define a new Saga and spin up a car service. And then I would do the same thing for flights, where I would say, make a flight, charge the payment, make a new Saga, and make those new services. So that's sort of comparable amount of work to where we were before, but I think this is where it gets really powerful, is now when we want to go and add trips, all I have to do is define a new Saga. I just say, like, these are the causality I want to enforce, and these are the invariants I want to enforce via this DAG, and then I just add it to the system, and I add some new API to my front end to kick off this start Saga in my SEC. And this is really powerful because we didn't have to go write a bunch of Pharaoh concurrency control logic. We can get this product to market we can get like the trips feature to market much faster just by having this sort of infrastructure already in place. Okay, so I really like Sagas because they have this great isolation of complex code. The complex code all lives in the SEC, and it's complex. It's not like terribly difficult to get right if you go and write it, but at least it's all in one place. As opposed to our microservices example where the complex code sort of lived everywhere because causality was spread and chaining was spread out throughout your whole system. It also gets more to the microservices and SOA belief of modular services, really. Like, this thing is only booking a flight. That's the only thing it has to know how to do. Whereas in our microservices example, it has to know how to book a flight, and it also has to know how to enforce the Pharaoh concurrency control mechanisms to make sure our payment invariants hold. And so this is a more modular service design. And really where I think it's powerful is now you truly have service composition. And it makes your designs and your services much more extensible because now I just add a new Saga if I want to use any of these things in some kind of new pattern or manner to enforce different invariants. Whereas here I have to add a whole new service, have new Pharaoh concurrency control mechanisms, and this gets really much more complicated. So I hope I've convinced you and given you some ideas of how distributed Sagas can make building and modifying your microservices easier. These slides will all be online. I will tweet them out after the fact, and thank you.